Welcome everyone, and thank you so much for joining us at Neo4j on our webinar today on graph thinking. My name is Corey Brickman, Marketing Programs Manager here at Neo4j, and I'm joined today by Andreas Kollegger, Product Designer here at Neo. Thank you so much for joining us, Andreas. And
thanks for having me today.
Thank you. Just a few housekeeping notices before we get started. You may ask questions anytime throughout the presentation by using the questions widget on the right-hand side of your GoToWebinar control panel. We'll go ahead and present to you for about 30 minutes, followed by a live Q&A session. And also keep in mind, we will be sending you a recording of today's session as well as the slides. So definitely make sure to check out our follow-up email that you'll receive later today. And with that, I will go ahead and hand it over to Andreas.
Awesome. Thank you so much, Corey. Thank you, everybody, for joining us today for this talk about graph thinking. My name is Andreas Kollegger. I'm a product designer with Neo4j, which is, of course, a graph database, which is why I do a lot of thinking about graph thinking. And why I think that graph thinking is sort of important for all of us to think about is that graph thinking, for me, is really, it's the missing link in your data. And it's true for everybody, anywhere. If you have data, you should be doing graph thinking. Graph thinking is going to improve everything about what you're trying to do with your data and what you're trying to achieve. And for me, when I first realized this all started years ago, before I was involved with graph databases, before I was involved with Neo4j. For me, the story about graph thinking and how I came to realize that there was such a thing started when I was doing international work in sub-Saharan Africa, and there was this place. There was this place called Challenge Clinic in Lusaka, Zambia. And I was super privileged and honored to be part of a group that was working in Zambia to set up the nationwide health information system. And I'm not a medical professional, I'm not a doctor, I'm a computer person, I'm a designer, I'm a technologist. But being able to work in this environment and understand some of the challenges that were there, and particularly the data that was involved, of course, helped me come to new realizations about things that I hadn't previously realized. And thinking about what we were actually trying to do, we were just setting up a medical record system. Medical record systems are pretty straightforward when you think about like the standard practice of it. Imagine going into a doctor's office, and the first thing you usually encounter, of course, is something kind of like a form that you've got to fill out, where in the sort of the language they talk about subjective data that you collect from the patient, where the patient actually says what's going on with them today, why they've come in, what their current complaint is, and maybe there will be some questions on the form about like lifestyle and other sort of subjective information that is the patient will self-report to describe what's going on, and that goes onto the form, generally in kind of open sort of text fields. To that, then, of course, there's always sort of objective data that's added. Objective data being things that you can actually measure, things that you've got instruments that you trust, that you've used to actually get some information, and now you're going to capture that onto the form as well. And this together becomes all the input for the current encounter with the patient to try to understand what's happening and what might be affecting what's going on. Now, when you're the doctor, of course, you look at that sort of input to the system, and you perform an assessment. You say, okay, great. The patient has come in. They've been complaining about this or that. We've done some tests. We've done some measurements, and I'm going to conclude that probably here's what's going on. Now, sometimes the here's what's going on is pretty obvious. If you've walked in with a, let's say, a broken leg. You probably have a limp. Perhaps your leg is at a funny angle. You can run an X-ray to actually confirm things, but the broken leg is pretty easy to understand. It's a very clear mapping there, and not very challenging. But that can get very complicated. And generally, actually, in these assessment areas, it's usually not just oh, it's obviously this. Here's what we should do in response. There's usually extra information that the doctors observe here and add to this field. And then based on their assessment and the data that they've collected, they come up with a treatment plan and say, all right, here's what we need to do to actually improve care for this patient, to improve their well-being. Now, once all of that part of the form is done, there's always another part of the form that gets added. Here in the States, of course, we're very familiar with these things, and it's true around the world that in addition to the sort of patient care aspects of a medical record, there are coding aspects to the medical record, where the coding aspects are things like ICD-9 codes, which describe internationally recognized codes for particular diseases and conditions. And then there are CPT codes, which describe precise procedures that might have been performed or should be performed for a patient. And often this is just used for billing purposes, at least here in the States. But this is used actually all around the world, whether or not there's billing involved, to try to have coalesce all the previous information that has been collected about the patient into some kind of a normal format that is universally understood. All of this data that's gathered into the medical record system is used for a couple different things. Of course, primarily you care about the patient care. You care about the patient who has come in actually getting resolution for their complaint. It's also used for decision support. This information, so before you decide what the plan can be, this information can be used to share with other doctors or with expert systems to actually figure out what the right response should be for the patient. And some of the information then gets kind of generalized and collected and aggregated and generally reported back to public health professionals who want to do sort of surveys of an entire society and like what's going on. So they're doing sort of aggregate summaries of all this data to try to understand, what indicators might be happening on the input side that indicate, diseases that are happening and the appropriate responses to those diseases. And even more generalized then, there's the people up at the top who are, in this case it was the WHO who had funding for a lot of these programs, who really wanted the outcomes. They wanted drop all the detail entirely, just tell me, are things getting better or worse in the country? And that's really what matters. And when you look at all of this data, this looks pretty straightforward. It's just fill out a form, do some analysis, take care of patients, and everybody's happy. We probably have variations of this in all of our day-to-day lives. There's sort of raw data that we capture, we think about it, and then we do something about it. As it happens in this particular circumstance, and I think every time as technologists that we try to write software or create systems that help these situations, the initial data that we capture, we realize is never quite enough. By the time it gets up to the public health people and even sometimes the WHO, they might realize that there's some information that's missing that they'd like to know about, and so of course they ask for more, and the forms and the data that you're capturing always gets more complicated. You end up asking more questions of the patient, you end up doing more tests, you end up gathering more kinds of information, whether it's x-rays and different electrocardiograms and things like that, and of course you're capturing more codes all along the time trying to generalize and understand what actually is going on. This is probably true in every system that we try to develop. You can imagine in your particular circumstance, if you're involved in a business, that really from patient care on up to the WHO, this maps to your users, your staff who are doing things, the management who are telling the staff what to do, and then the board of directors or perhaps your shareholders who care about how well the business overall is doing. So the actual context, of course, is just this is what I was working with, but this is the same kind of dynamic that happens everywhere in every business in every kind of industry. So there's one part of this that I particularly cared about when I was building the system and working with people that was intriguing to me, and it was this box here. It was the assessment box, because the assessment box, as I was saying earlier, is actually where often there's extra information that the doctor observes that they fill in here as they're trying to understand what's going on with a particular patient. So I want to know more about that. I want to know, how does that actually work? How do you perform an assessment? And of course, the inputs to the assessment are the current data that's on the form. You look at prior history of the patient, and of course, maybe you apply some direct knowledge that the doctor has about the local context. All of these things together influence probably what's going on. So this is information that is, some of it's on the form, some of it's older information that you might have captured, and then some of it is expanding the scope of what's actually there. And looking at all that data, of course, the way that assessment works is that you think, how is this data actually related? And in the data that's related, are there patterns that emerge so that I can understand, like, oh, actually, I've seen this pattern before where a patient comes in and says this, and then we notice this reading, and then actually it ends up being that this is disease over here is what they actually have, or this condition is what they have. And in order to, find all the possible patterns, you have to try to figure out which of these patterns actually matter. There might be some patterns that, of course, look really interesting, but don't have any bearing on actual outcomes or relevance to actually helping the patient, resolve what's going on. So when you're doing this assessment, then the actual activity of assessing, of looking at the data and thinking about the data, creates new data. It's actually making connections between the data that's there and figuring out how the data is related. And then those relationships themselves are information. It's new data, and it's the relationships that actually are what determine what to do next. So that's where the real value of all the information is. And it's in the part of the form that is free text, that isn't actually captured anywhere. So that means that there's actually some data missing. So looking back at this, of course, the data that's missing ranges from data that's, general purpose, like medical knowledge and epidemiology, understandings of cultural norms and behaviors, environmental factors for like where the person might live. Of course, agricultural practices might come into play, and then you care about things like patient relationships, their immediate family, their even the friends that they have, sometimes they're co-workers. So understanding what's happening with all of those people can help you understand what's happening with a particular patient. And then the doctor relationships as well also matter. You may not, as a doctor, have seen this particular pattern of things before, but some parts of it, somebody that you know might have seen it and have some insight into what might be going on. So having doctor relationships also captured is important as you're trying to actually give patient care. And then there's related research and on and on. And as you start to think about what data might be relevant, what data might be related to what's going on, you realize that there's much more beyond what you've actually captured that's important. And so you can continue to sort of follow this idea and say, okay, well, what else is related and what else is related? And when does that actually stop? How much data do you actually need to actually help a patient have a positive outcome? If you would ask Tim O'Reilly, he's made a general comment about sort of the world of technology and data, and he said, the person with the most data wins. He's making this observation really about what we all come to understand as the sort of the trend of big data. The big data phenomenon now is our realization that the available input sources that we have, that we can actually capture the sorts of forms, as it were, that can input data into our systems is growing incredibly. And more than that, the relationships in all that data is also growing. So it's both a volume of data and an increase in the complexity of the data. And Tim O'Reilly was suggesting that if you want to have the best outcomes for whatever it is you're trying to do, if you want to win, that the more data you have, the better you're going to do. It's certainly true in patient care that the more you know about that patient and the things that are affecting that patient, the more likely you'll be able to understand what actually is going on and what you need to change or what they need to do to actually have a better health. So what data is actually relevant then? Instead of how much data do you need, what data do you need? And the way to answer that is to think about two things. You look at how close the relationships are between the data. So as you're making these data relationships, you think about the central data about what you care about that person, right? So in the case of patient care. So for any data that you want to bring into and consider, the further away that information is from the patient, the less relevant it really is. You can think about the family relationships, for instance, that the immediate family probably matters a lot. Blood relationships matter, quite a bit. But as you get beyond, first cousins and second cousins and further, the further in a family tree you go, the less relevant probably that information is. So the closeness of relationships matters a great deal for determining how relevant the data is. And then in addition to that, you have to consider the number of relationships between data, and that changes the importance of that kind of data. Between the relevance and the importance, patterns emerge. Of course, when you've got patterns, naturally, that leads to pattern matching. And it naturally leads to pattern matching because that's what actually exists in the data, and that's because how we are wired to think. Pattern matching is the way that we naturally think about the world around us. That's what we are built to do as humans. We often think about, that people just like to think in terms of sets. We like to categorize things and put them into little pigeonholes. But the reality, of course, is that every time we categorize things, the category doesn't matter as something to separate and isolate the data, but as a way to actually say, okay, actually, not only do I know that this piece of information is part of this category or part of this set of things that I know about, but I know how this set of things relates to this other set of things. And actually then the patterns of how the sets themselves relate is relevant. And you take that general idea of the general patterns that are emergent, and you apply that to local instances of data, and that's how you have positive outcomes. When you look down into like the brain, how the brain actually works, of course, we realize that like the patterns and the connections in there are functions of the neurons that you have, which number in the billions, and then the synapses, which connect all the neurons, and they number in the trillions. That sort of ratio of like things in the billions and things in the trillions between the nodes, as they were the neurons, and the connections between them being trillions, that's common in every connected data set, whether it's your brain, whether it's patient care, whether it's any industry you might be. There are always more relationships than there are things being related, and that's where the real value is. You can think about the internet, of course, and if you want to find out information about the internet and do work with the internet, the individual pieces of information that are there, the individual pages are interesting, but really it's all the connections between them that are far more interesting. That's what lets you know what's great about the internet and where to find things. You can look at things like, corn, actually. And if you look through genetic history and the ancestry of a single corn, that itself actually fans out into this fascinating, cross-pollinating world that kind of looks like a tree, but the tree is actually connected within itself, which ends up itself then becoming a graph. And of course, there's more immediate personal things like, this happens to be my LinkedIn network, and that also just has more connections than it has individuals within those connections. Because of course, there's the people that I'm connected to, but then they're connected to other people, and then those people are connected to other people, and on and on. And that creates this really lovely, expanding universe of information that exists in my LinkedIn network. So why is it really important? Of course, this comes around back to graph thinking, that thinking about relationships and patterns in the relationships, and trying to do pattern matching. This is what graph thinking is all about. Graph thinking has created some of the most successful companies in the world. LinkedIn, for instance, hasn't been around forever. There was Monster before there was LinkedIn. And LinkedIn didn't start off as a job search site, but that's actually where its greatest value is. Job searching on the internet started with companies like Monster, and Monster pretty much took what we did in the offline world, looking through classified ads and having listings of people who have job offers, and just they digitized that. They made that available with a nice web interface so that you could easily search for things, job listings you wanted to, and mark off the ones that you liked, and then send in your resume and kind of help that whole process happen. And that was pretty good, but LinkedIn realized that they were creating this professional network, and we know that if you're looking for a job, the best way to find a new job is to work your network, to actually ask people that you know who might know somebody else who works at a company that you want to work at. That's the way that you're going to get a new job. That's the way you're going to get good recommendations, far more likely than you're going to by just sending in a resume blindly to some company that may or may not know anything else about you. And because of that, LinkedIn has risen and become this incredibly powerful force, whereas Monster has struggled a little bit. The other story that is about connected data that has made a huge difference was that before there was Google, before we just kind of assumed that to find things on the internet you would just Google for it, there were other search engines. There was Alta Vista, there was Lycos, there was an entire few dozen candidates of people who tried to provide search for the internet. But it was Google who had the simple insight that the relationships between the pages are what actually mattered. That it didn't matter what was in the content of the page itself, what the page claimed to be an authority about and have the most relevance for Google realized what that really mattered is that if other pages actually thought that that page was important about something, that the relationships would actually determine what the ranking was. So this was the basis of Google's ranking system, and PageRank is what they built their entire search engine around, and that of course has created looked at the internet as a giant graph and doing graph search on that. They have since taken that idea even a step further and realized that in order to do the best pattern matching, when you've got a question, rather than just doing simple keyword matches from that into the patterns that are in the internet, you first want to understand the knowledge that the knowledge graph that is represented by the internet, and use the question that you've asked to understand what other things are relevant to that, to have an even better understanding of like what keywords actually might be related that actually solve whatever it is you're trying to look for. Perhaps less obviously, the same dynamic was true even for banking. Banks prior to the internet always had a challenge with fraud. Bank fraud is one of the biggest challenges for banking. And online banking, of course, is incredibly frightening. If you have people that you don't know anything about, that are completely anonymous, you don't even have them physically in front of you exchanging monies, that it's much easier to commit fraud because things are just invisible to you. And if you can mitigate those risks of fraud, then you can actually provide online services. What PayPal did, of course, is it created a graph of transactions, and then in looking at the graph and being able to analyze the graph and looking at patterns of normal spending and abnormal spending, and also group behaviors that were merged, so-called fraud rings within spending, you could determine whether any given transaction fitted a pre-existing pattern of normal expenses and was probably fine and was okay, or it had signs of being part of a pattern of fraud that should then be actually prevented. And because they could mitigate fraud, they were able to actually offer online banking services in a way that was cost effective. So if we're thinking about graph thinking, what exactly is a graph in the graph thinking? We, of course, have seen a bunch of examples about this before, but let's think about it a little bit more directly. A graph is just a way of representing data. And you can represent data in a bunch of different ways. So looking here at basically the same set of data two different ways. Here on the left side, you can take a jumble of data and arrange it into sets. And in those sets, you can then do things like aggregate operations to find out the averages of things or the total number of things. And that's basically what you do when you've got a relational database. A nice orderly set of data that you can reason about very cleanly. And this, of course, is a very powerful model. You can, if you're good with relational databases, you can model anything that you care to, and answer really useful questions for it. But generally, this is good for things where you have well understood data structures that aren't changing, that you don't need to continue to add things, that there aren't lots of special cases. You want things to be very kind of nice and neat and orderly. If you think about my first example when I started with the medical information records, the fewer questions there were, the fewer free text form fields there were, that fits much better into a sort of normal way of doing work with a relational database. And when you have data that fits into nice little boxes, and you can check all those boxes off and fill them in with data that is validated. You can use that for doing solving known problems with discrete parts of the data where there's not a lot of connectivity, where what you care about is actually getting exact matches for things, or finding ranges of things, or getting sort of reporting data on what's going on. So back to my earlier example, the kind of information that the WHO actually cared about is more just reporting data. They'd be perfectly happy with a relational database view of the world. But we know that the actual data in the world is much messier than that, and that every time you try to organize data and fit it into some boxes, you're almost always throwing some information away. Another way to do it instead is to use something like a graph database. So you take the same data, and instead of trying to fit everything into particular boxes, you say, all right, let's leave each individual record as it is, and we'll just create relationships among that data. and then we'll work with it as it is. So each record now can represent whatever it would like to. It can have common sets of fields. It can have common sets of relationships, but it can also have unique fields, and it can also have unique relationships that other parts of the data maybe don't have. This is really good for dynamic systems, where the data topology, as it were, is difficult to predict or continues to evolve, or that local subsets of it are, are different than the general case. In particular, this is true when you've got dynamic requirements, that evolve as your business evolves. And while we'd all like to just have, a market and a marketplace and customers that are nice static, and you can understand them all, and finally predict what everybody needs and then give it to them, we know that people's needs and people's interests and conditions in the world continue to change. Of course, we live in a dynamic world. The world is messy, so every business is an evolving business. So when you look at things from a graph perspective, you shift your perspective a little bit so that rather than trying to categorize everything and try to have everything be nice and neat and orderly, you embrace the messiness of the data a little bit, and you allow the data to really express the problems through the relationships rather than trying to capture everything into records directly themselves. So now I'm going to drill down a little bit into what the property graph data model is, but we won't get too technical today. So a graph is some data records and then connections between those data records. For instance, if you're looking at a map system, you could look at traffic that's driving on some roads, and that road has some lights. If you happen to have a hotel reservation system, that means you've got some hotels. Those hotels have rooms, and those rooms have availability according to some schedule. All of this would also be mapped very neatly into just a relational database, no problem, right? So as long as you're keeping things very simple and very neat and orderly, that can work the same. What's interesting is when you start to combine things a little bit. So if we started here, for instance, with what is a social network, you've got some people who know other people, and not only do they know other people, but for some of them, you've recorded extra information about the relationship. You can say that these two people have known each other since 2012, for instance. In this graph model that we've been looking at, this property graph model, we talk about the connections between the data as being relationships. We talk about the individual records of data as being nodes. And on both the nodes and the relationships, we talk about them having properties. Now, the fun part is that once you've got things in this kind of form, you can continue to add data as appropriate. So you can just expand the social network a little bit. You can add extra dimensions to it and saying, oh, okay, in addition to people who know other people, we can introduce, where they've gone to school. And so you know that you've got classmates at that point without having a direct relationship. There's an implied relationship there. People also, of course, have co-working relationships, and the co-working relationship is a tertiary relationship from happening to both work at some location. And if what you care about is thinking about co-workers, then you could actually take the fact, you could do a query that says, oh, actually, people who work together at the same place, let's create a direct relationship between those people so that we can then reason about co-workers rather than just finding out where people work. So you can continue to elaborate on this graph, adding things, more companies, more places where people went to school, and intermingling. Then you could even start drawing connections between the schools themselves. You could say that some companies were the founders of some companies had gone to some school. So you could for instance, credit Stanford or Columbia as having been founders for, let's say, Google, or I can't remember who's come out of Columbia, but I'm sure there's examples there as well. And you can continue to add different dimensions to the domain, and as you're running queries, add that information as is appropriate for what you're trying to answer. As you continue to elaborate, all graphs, of course, continue to get more relationships and more information into them and become this lovely giant pattern of just interconnectedness. Okay, let's take a few moments here just to be a little bit more practical about what graph thinking actually means. And we'll look at a couple of different examples about things like real-time recommendations, doing master data management, fraud detection that I alluded to earlier, graph-based search, which is similar, of course, to what Google does, IT operations, and identity and access management. So if you're thinking about real-time recommendations, and recommendations actually is what I wanted back when I was looking at medical information systems in sub-Saharan Africa. What I wanted to actually build was systems that not only captured the inputs, but also were able to make recommendations to help decisions for caregivers who were maybe not necessarily doctors that were working in the field who needed a little extra information about, like, what the best plan could be for a particular patient. The plans that we could recommend there are the same as doing a product recommendation or doing a matchmaking recommendation or anything else. The same algorithms actually apply. That's one of the lovely things about graph thinking, is that if you understand generally how to do real-time recommendations, you can apply that to any graph you might have and actually take advantage of it. In this simple example here, this would be like a product recommendation example where you've got people who have viewed different things and bought different things, and it looks like we've got a couple people who have viewed this bucket, but only one of them has bought the bucket. But it looks like they're all buying garden supplies. You can then generalize even on the products themselves and see that all of these things are part of the garden department, and you could see that among people who know each other. So if you added to this both the social network and the product sort of categorization, you suddenly can build a very rich recommendation system that looks for patterns of people who know each other. So you're doing matchmaking amongst the people who have bought this thing, have also bought this other thing. And then that's how, like Amazon, for instance, or Walmart or anybody else actually makes useful recommendations for products. Thinking about doing graph thinking with Neo4j, that is in fact what Walmart's starting to do with Neo4j. So that they can actually do product recommendations. Another way of thinking about graphs is graphs with master data management, where master data management means lots of things to lots of different people, but often it starts with just taking what is sometimes a very neat, orderly tree of an organizational chart that gets very complicated. We've got organizations that spread across the globe and have lots of different departments, and so now you care about where people work in addition to who reports to whom. But then you also care about, amongst those departments, the different departments work together, even if they don't have direct reports that overlap. And you want to capture all that information in the master data management so that you can actually help people work together, so that you can actually understand when you've added a load to somebody in the organization is going to suffer. This is something that, in the simple org chart version of master data management is pretty. This is so useful that this is what Cisco actually has adopted Neo4j for in their Cisco HMP. It's the single source of truth for all of the hierarchies in the organization within Cisco. The fraud detection that I had talked about a little bit earlier is a beautiful example of graph thinking where, in order to understand potential fraud, you look at group behaviors, and so you look at information from potentially fraudulent people, and you see whether the information that somebody is using is also being used by somebody else. And if those people are interacting in ways that they have shared partial information but disparate, let's say, locations, the more financial instruments that they have that are in common, while their sort of purchase dynamics are different, that can sometimes indicate fraud. You'll end up seeing rings of this where people they'll share, for instance, fake social security numbers and use those to open up accounts fraudulently, and then perhaps they'll even claim to live at the same location, but they'll always ship to different PO boxes. And by looking at all the abnormal patterns rather than the normal patterns of how people who share a credit card, let's say a husband and wife, and when they buy things that they'll ship to their home or to one of their offices, that you can look for the patterns that don't match that and realize that that's probably fraud. Right, and this is something that, of course, graph databases are fantastic for, and importantly, for fraud, it's something that you want to do in real time. It's not something that you want to do sort of in a batch analysis job. By the time you've spent an hour or two looking at some fraud, the fraud's already happened, and you just have to now try to catch up rather than stopping it as it's happening. Graph-based search I talked about a little bit before, about how Google actually sees the world. That same idea that Google uses, you could use in any domain that you've got. If you've got a knowledge base, or you've got content management systems, or you're trying to do digital rights management or something, graph-based search is what lets you take advantage of all the relationships between the pieces of content themselves, and then use that to actually find things that matter, rather than trying to rifle through all the information in a raw fashion looking for things. For instance, this is what Lufthansa does for their next generation in-flight entertainment system. Network and IT operations is another good example of graph thinking, where if you have a network, of course you've got network equipment which is physically connected in different ways, but then often in addition to that, the physical connections, you've got logical connections between things, because you've got pieces of equipment that are hosting software that software is running on. You've got pieces of equipment that are actually providing connections for of course communications, so the internet, for instance, right? And so between the physical connections, the network connections, and the software connections, as it were, this becomes a very complex graph of things that, if you're doing things like managing let's say a telecom system in a country, you want to know before your customers know that taking down some power supply somewhere isn't going to disable half of the East Coast. If you do the network analysis of everything, you'll be able to realize that this particular power supply, for instance, in this very small graph, if you took that down, this entire network would go down, and everybody would be out of operation at the moment. So graph thinking lets you actually focus on all those relationships, understand what pieces of equipment are the most important and need redundancy, and if you need to take something down, you can make plans for how to reallocate resources before you have something actually go out of service. HP actually uses that thinking in their sort of built-in network topology analysis system that they provide for big telcos. And finally, thinking about identity and access management, that also ends up becoming something that expresses a graph, that the relationships are actually what are most interesting when you're thinking about identity and access management. Because there's, of course, you've heard about the network of trust. That itself is a graph. In addition to the network of trust amongst people who trust other people, there's the things that those people have access to. So there's both authenticating people, there's authorizing people. These trees end up emerging, and the trees, of course, are interconnected. That ends up creating a graph, and the easiest way to actually manage that entire graph is with something that is a graph database. That's something that UBS has done superbly in an application, such that they actually got an award a couple years ago for a fantastic identity and access management app that they had put together. Okay. I don't want to run too much longer. I know that I've maybe gone a little bit further than I wanted to. So I just wanted to wrap up quickly now, so why graph thinking? Why does this actually matter? Thinking back to where I started, I suggested that there's an intuitiveness to graph thinking, that it's a natural way to actually think about the world around you. That pattern matching is what we naturally do as humans. If you have a graph database, for instance, that sort of embraces graph thinking, you also then get the benefit of speed, that you can get questions answered in real time rather than having to do batch operations for things. And you get great agility if you have adopted graph thinking and you're using a graph database, where now you don't have to pre-compute a bunch of things, or worry about having data migrations all the time, because you can have a data model that evolves as your needs evolve. So the intuitive course, that ends up showing up in things like, we like to say that graphs are whiteboard friendly, that whatever you happen to draw on a whiteboard when you're explaining some problem to somebody else is the actual data that you save in the graph database. So you don't have to actually do some mapping and say, okay, the thing I'm thinking about, how do I store that in the database that I have? You just store it directly the way you naturally think about it. The speed comes out mostly as a function of having a database that is is oriented around doing work with relationships. And if you focus on doing relationships and you have data structures and storage systems that are optimized for working with relationships, the queries become, massively faster and often take, a fraction of the amount of code for expressing the same ideas. Yeah, you get comments like this, and the classic minutes to milliseconds performance switching from a relational database, or other NoSQL solutions to something like Neo4j. And finally, of course, there's the agility, where you've got this data model that fits the way you already think about things, and that can expand gracefully. And if you're using a graph database like Neo4j, you get a query language that is designed for thinking and expressing ideas around connectedness. And I'll mention Cipher just briefly here, because I love this. This is a fun one that, if you want to think about relationships in a relational database, you could end up with queries like this, where you're just doing all kinds of crazy joins in this very hard to read, very large chunk of code. That same chunk of code boils down to this really super simple Cipher query, where now you're doing a pattern match for some boss that up to 3 levels deep manages some people under them, some subs, and those subs also have some reports underneath them. And where the boss's name is some John Doe, and you want to find all the sub names and just count up how many reports they have directly to them. That's it. Those are equivalent queries. But on the right-hand side, in the Cipher version of it, in the graph-oriented version of it, it's very natural to understand what's going on there, and it very directly expresses, the query rather than being buried in a bunch of joins. So that ends up meaning that you spend less time writing queries. It's easier to debug because you can actually read these things, and you can make more progress with, actually solving problems rather than just trying to figure out how to write code. Okay. I'm going to skip over the Cipher part here and actually go towards the end because I know we're running late. So users do love Cipher. Cipher is pretty fantastic. We've got other webinars that talk specifically about Cipher and dive into some of the technical details, and I'm not going to get that today. I just want to conclude with this statement here, that graph thinking means focusing on relationships, and when you focus on relationships, what you do is you turn data into information. And the connections between data, when data is isolated, it's not yet information, it's just raw data. It's sort of a bunch of rocks sitting in a pile. But when you actually apply graph thinking and you take those rocks and you actually work with them and put them together into a building, you've now created something. Now you've created information, and that information then expresses you find meaning in that information by looking for patterns amongst the relationships, and that's the essence of what graph thinking is all about. So it's all about relationships and patterns. Okay, thank you so much for listening today. I know that we've run over a little bit, but I hope we still have time for a few questions.
Perfect. Thank you so much for that excellent presentation on graph thinking, Andreas. We very much appreciate it. We will go ahead and open up our live Q&A session now. So thank you so much to the audience members who have already submitted questions. As a reminder, you can still go ahead and submit your questions using the questions box on the right-hand side of your screen in your GoToWebinar control panel. And with that, Andreas, I will let you go ahead and take over asking and answering some of those questions.
Okay, thank you, Corey. So I'll give you all a minute or so here to add some questions to the list that's here. And I'm going to try to pick out ones that are generally useful to people. Although, of course, feel free to ask me anything. And I think after this, of course, you can always, get in touch with me through email or Twitter if something occurs to you, later on in the day. So let's see, for general questions here. Okay, so there's the classic comparison of the burden of relational modeling, or not the burden, I guess here it's expressed as, a relational model can really express everything. It is a general purpose system. Why is it that graph modeling is easier if graph modeling is messy? And I guess what's really at the root of this question is like, with graph modeling being dynamic and being open and being very expansive, there's sometimes some concerns around it being too not knowing what to expect, that people like the comfort of having a schema so that you can sort of control the data that gets put in and know what kinds of questions you can answer before you start getting input. And I guess the answer to that is simply that there is still schema effectively within a graph. You can do a couple things within the property graph model. I didn't show it today, but there is also this notion of having labels on nodes so that you can, for instance, say that this particular node represents a person. You could also add a label saying that this person happens to be a citizen of France, let's say, or of the UK. And based on them being a citizen of the UK, for instance, you could say that, well, I expect that people who live in the UK will always have a national insurance number, I think is their registry number. And so you can make some kind of like lightweight assumptions about the data, the same that you could in a relational database. But the thing is that you don't have to pre-decide all of the data that's going to fit, so that you can sort of evolve the data over time rather than having to have a perfect schema up front. So that's part of the advantage with graph thinking, is that you can let go of some of the stress, I suppose, of having to be predictive of all future possibilities. You can just start off with what you know today, and let the questions that you want to ask sort of drive what extra things you want to add to the data set, without having to worry about completely changing the data set every time your perspective changes. Actually, I'm sorry, I'm going to stay on that for just a moment and think back to my earlier, my first example about the medical informatics. If you remember, I was showing things that the applications being served were everything from direct patient care all the way up to the abstract reporting to the WHO. In some systems, of course, you solve that with a systems approach, where what you do is, rather than having one database represent everything, you have derivative databases, essentially, where you kind of do some processing on one database and you send it out to other people, and you have derivative databases that those people then work with. The beauty of the graph is that you can have everything all within just the graph natively. So let's see what other questions are coming up that I should try to get to. Yeah, okay, so there's some questions about Cipher, I guess, as well, and pattern matching in Cipher. I think the best way to go about learning more about Cipher and what's possible there is by showing up to, I think we have webinars around Cipher specifically, and I know that we do full-day training classes, and in, April, the end of April, if you happen to be within distance of the UK, there's going to be a great event there, a Graph Connect conference, where you'll be able to meet with graph experts and learn everything you could possibly want to know about graphs and programming with Cipher. They run some graph clinics during that as well, so you can just show up with a notebook of questions and talk to a graph expert and get them answered directly there. Okay, actually, I think that's maybe all I'm going to answer for today. Everybody, thank you so much for spending this hour with me. Please feel free to reach out to me if I didn't answer your question. Go ahead and get in touch with me. Corey, I think, are people getting my email address, or what's the best way to do that?
Yes, what we can do is actually, we've got a log of all of the questions that were submitted, so we'll make sure to actually go ahead and email you directly with the answers to your questions. So if you have another one on your mind, go ahead and type that in and send it to us. We'll make sure to respond to you with an answer. And I did also want to comment, since there were a lot of questions about Cipher, we will have upcoming introductory webinars on Cipher, and also a really interesting webinar on Cipher specifically for SQL developers. So if that's of interest to you, you can check out our webinars page, neo4j.com/webinars. That will be up by the end of this week. So again, I just want to thank you, Andreas, so much for that presentation, and thank you everyone for joining us. We'll go ahead and send you a follow-up email with the slides as well as the recording, and we do encourage you to check out our webinars page and sign up for further informational webinars in the future. And thank you so much for joining us.